Hi, and welcome to the third section. It's a statistics thing. In this section, we'll see how R can be used to perform statistical analysis of data and visualization, starting with familiar operations and moving to more advanced methods. There are 5 videos in this section. We begin by doing some basic statistics using R to see how it's done. Then, in distributions, we see how we can work with a range of distributions, both generating samples with them and estimating parameters given data. We end by seeing how we can create a football model, simulating the expected results, since we know that goals follow a Poisson distribution. In its time to get graphical, we see how we can plot our data using standard plots, as well as some fancier ones. In plotting to another dimension, we introduce ggplot2, which lets us move to beyond traditional plotting by being able to not just map fields to coordinates, but colors and more. Finally, in facets, see another neat way to see the impact of a field, plotting multiple images as only one field is changed. Here, we're at the first video of this section. In this video, we look at how to use R to compute summary statistics, how to simulate the lottery with statistical functions and compute the odds of winning it, fitting a model to global warming data to see what we expect to happen, and the huge range of functions available in R. Using sample, we can pick 100 numbers from 1 to 10,000 with replacement. And we can see that we have 100 numbers, they're from 1 to 10,000. We can also pick 100 numbers which are all 5,000. So we put that into constant numbers. And we can see here that they're all 5,000 and there are, well, roughly 100. We can then look to see what the average of these numbers are. So the function mean, with my numbers as the argument, tells us that the average was 5,185 for my numbers, and for constant numbers it's 5,000. Now my numbers was randomly picked. Half the time it's going to be more, half the time less. We can look at the median. Again, for constant numbers it's 5,000. My numbers it's slightly more. And then we can look at the mode. Here we get an unexpected response. So the mode tells us which element appeared most often. So for constant numbers, that should be 5,000. For my numbers, it should be all of them, because we're picking numbers from 1 to 10,000 and we're only picking 100 of them. So no number should really appear more than once. They're all joint, most likely to come up. One of the strengths of R is the community. So basically, if you have a problem, many other people have had that problem before, a long time ago. So by just going R mode, there were multiple pages and they had multiple solutions. So this is roughly one of them. I'm just creating another variable x, which has elements a, b, and a. Now a occurs twice, so the mode for x should be a. Now the solution I'm using involved writing your own function. I don't know this originally came from, because the person I saw it from mentioned that they saw it from another web page. So I don't know who did it the first time. But we can just define this function, and then this is more the function that I'm interested in. So mode, the default one, the one that return numeric, just tells you what type of data you're looking at. So it's not the statistical function that I was expecting. So this new function mode is. So if I go mode x, it tells me the most common element of x is a, which it is. Next, I'd want to look at variation and distribution of the data I'm looking at. So I might want to look at the range, which is the min and max of what I'm looking at. So my numbers has a min of 109 and max of 9,761, while constant has 5,000 for both. I can get more detail using quantile. So 0 and 100% are the min and the max, 50% the median, and the other two are the quantiles. So I can see the data seems to be quite uniformly distributed, since the gaps between them are the same. I can also look at the variance, the command for which is var. So we can see that for the constant numbers, the variance is 0, as we'd expect, since they're all the same. The command for the standard deviation is sd. So I can see the standard deviation for the constant numbers is 0, and for my numbers is 2823.584. R also has statistical functions. So for example, the Euro Millions changed recently. So now we have to pick 5 numbers from 1 to 50 and 2 from 1 to 12. We can see here we need to pick 5 numbers from 1 to 50 with no replacement. So no number can appear twice. And we want 2 lucky stars, which are from 1 to 12. Again, with no replacement, which is the default. So I just set my selection into main numbers and lucky stars, and I can see them. So here are 5 numbers from 1 to 50, no number occurring twice. Here are 2 numbers from 1 to 12, no number occurring twice. If I wanted to figure out how many possible numbers we could have, then I'd multiply these two. So I'd work out 50 choose 5, which tells me the number of possible ways that I can pick 5 numbers from 50 without replacement, and then I'd multiply that by the number of ways that I could pick 2 numbers from 12, since they're independent. So now I just work that out, and it's 139.8 million. So far, we use the included data. So for example, when we're looking at the Titanic dataset, and then we loaded up data when we were looking at tennis, reading it from a file. Here we're going to use Quandl, which is primarily about financial data, but there are many data sets. And there's a package, Quandl, which we first need to install. So you just go Quandl, install. Now I've already installed it, so I don't need to. Then we just tick the box here, and now we can use it. So we just go temperatures is equal to Quandl EPI 74. So each data set has a code. So all we need to do is enter the code and we can download it. So I just run Quandl EPI 74 and then plot it. So this is the global warming data set, showing the average temperature from 1880 to 2010. We can set Y to the temperature field of this variable, and then X to 131 to 1. The reason I do this is because the X-axis is in a date format, and setting X to just the numbers 131 to 1 is easier to fit data to. So having set X and Y, I'm just going to plot X, Y, and we can see it's the same data. Then I can fit my model. So I'm just going to fit a straight line through the data, which I can plot using AB line, and there we have it. So the trend is clearly up, and our model fits the slope of the trend. We can also see that it's pretty noisy, that we have periods where the temperatures jump a good bit away from the trend line, but then pull back, and even below the trend line, before continuing the upward trajectory. So that would suggest that, okay, at the moment, good bit above the trend line, but I wouldn't be surprised if it fell and took 30, 40 years before we hit new record highs. That's the kind of data this is. And having this data, we can make these kind of statements. I like this data because it's an interesting problem, and also because it shows how much we can do using R without having to do any work. All I had to do was say the name of the data set, and I could load it up in one line. Then I could plot it and see, oh, the temperature seems to be rising. Then I could fit a model to it with one line and plot that as well. So with just a couple of lines of code, create my global warming model and make forecasts about what I expect the average temperature to be in the next 10 years. R is a statistical package. So yes, there's a programming language there, as we looked at in the last section. It was created and it's designed to do stats. We can get a sense of what it can do by just using help. And as you can see, it does a lot. So it has ARIMA, ANOVA, autoregressive models. It has multiple distributions, chi-squared, f-test, gamma, geometric, you name it, it's there. And if it's not, there are the thousands and thousands of packages. So for example, there isn't any Bayesian stuff here, but there are many, many packages like RStan, which is one of the latest Bayesian engines out there. In this video, we looked at how to perform some summary statistics before simulating a lottery and fitting a model to global warming data with just a few lines of code.